What about if A had been equal to B, though? If A is equal to B, if the two poles are of the same height, then the function t becomes that, with this as the derivative. And again, we will cancel out the 2's, etc., etc. Set that equal to 0. Add this portion to both sides. Square both sides. Multiply both sides by something so that we don't see negative powers. Without expanding these c minus x quantity squared parts, let's just distribute it over here. And here, let's distribute the x squared. Then we see that we can cancel the common x squared times the quantity c minus x, all of that squared. Furthermore, since a is strictly positive, then so is a squared. Divide both sides by a squared. Take the square root of both sides. X is equal to plus or minus c minus x. Now, by the way, remember that x is not negative. And since c is greater than or equal to x, c minus x will be non-negative. So that when I take these square roots, then we don't have to worry about imaginary numbers. Okay, so this means that either x is equal to c minus x, or x is equal to negative c minus x, giving us either 2x equals c, or 2x equals negative c. C was strictly positive, which would make 2x equal to something that is strictly negative in the second case. And that is not possible because 2 being positive and x being non-negative then this would have to be non-negative. That cannot equal a strictly negative. So we reject this. And we just have that 2x equals c, so that x equals c over 2. Let me write that up here. That would be halfway in between the two bases. We put in 0 to the first. 0 squared 0. A squared plus 0 is 0. We've got the square root of a, but a is strictly positive, so square root of a squared is a. Put in 0 here. C minus 0 c. C squared then. We have the square root of a squared plus c squared. And at the other endpoint, we put in c for x. C minus c is 0. 0 squared is 0. A squared plus 0 is a squared. Take the square root of that non-negative a squared, and we just have a. Okay, so we're looking at the same thing at either endpoint when a equals b. What about when we put in c over 2? For x. C minus c over 2, that would be 2c minus c all over 2, so just c over 2. In other words, we've got the same thing under both square roots, so 2 times that. So comparing what we have at the critical value to the endpoint, same thing at either endpoint actually. So again, let's square both sides. Over here, splitting up the squaring to the 2 and then the square root factor. Let's combine the like terms here. And square the c over 2. Distribute the 4. Cancel our c squareds. Subtract 2a squared from both sides. Subtract 2a squared. 2 is positive, a is positive. Dividing both sides by 2a. All right, so c, strictly positive. 2 squared, strictly positive. Added to a squared. That's something bigger than a squared. And when you take the square root of something larger, you get something larger. Also take note that if we had put in b here as equal to a, combine those like terms in the denominator, remembering that a is strictly positive, so canceling out, we get that c over 2. So really, even if a does equal b, then we can say that for this value of x, that it will minimize the function t. This is giving us an expression in terms of the heights of the poles and the distance along the flat ground between the two poles that will minimize the total length of the wires. But hold on, we're not done yet.